So now we're going to talk about formation of the solar system, and this will take several different chunks. First of all, we need to talk about how do we know what we know about formation of the solar system. What can we observe that gives us clues to what the solar system, how the solar system formed? Basically, its present structure must be formed during its formation, so we must be able to see clues within the present structure that give rise to how it formed. And so what we can currently see is the dynamics, how do things move in the solar system, where are they located, and the chemistry, so what materials are in the solar system and how is it distributed. We will do the chemistry next week. This week we'll be talking about the dynamics of the solar system. So what do we know? Well, the planets all revolve around the Sun in a counterclockwise direction. They nearly all orbit very close to the ecliptic. That is to say that basically the most offset are no longer considered to be planets. They nearly all have very close to circular orbits. We've talked about Mercury in homework, which has the most elliptical orbit, but they're still very circular. And they nearly all rotate in that same sense that they're going counterclockwise. There are a couple of exceptions, which we'll come back to. The orbits are fairly equally spaced, or regularly spaced, not equally spaced. But also the satellites, that is the moon, the moons of Jupiter, Saturn, and the other planets that have moons, they all orbit their planets in a counterclockwise direction. The planets have most of the angular momentum within the solar system, but comets come from all directions. However, the short period comets tend to be much more like planets in their orbits, although much more elliptical. The long period comets have much longer orbits. And so we need to be able to account for all of these things in any description of them. And so we come to the solar nebula hypothesis. This is the idea that the solar system was formed from a large cloud of gas and dust that collapsed and contracted under gravity and gave rise to the solar system. So here we have a large cloud that has a radius of about a light year. It is slowly rotating, but it doesn't need to rotate very much. In fact, it only needs to have very small spin. And then when it contracts, it gets to being much smaller, so the main part of the solar system would be within about 100 AU, so this is out to the edge of the Kuiper belt, and it still has that same axis of rotation. And so this is the idea that this was in fact originally thought up by people like Immanuel Kant, and it is fits well with the observations that we can see. And so there's this idea that you have this thing that contracts under gravity, and as it contracts it heats up, and so you end up with this disk shape and a bulge in the middle where there is a proto-sun forming. So we need to get the sun to form, we need to get the planets to grow from a disk, and so we need to figure out how do we get this cloud to be flat, so it's disk-like, and how do we get planets to form in it. Let's start with how do we make it flat. Well, if we have a collapse under gravity, here we have a cloud, it's collapsing, and it's spinning about this axis here. And it's collapsing under gravity, and it has energy that is given by the kinetic and the potential energy. As it gets smaller, that is, as it collapses under gravity, you're converting potential energy to kinetic energy. And so, as you are collapsing under gravity, your particles are moving faster. But as the particles move faster, their temperature is higher. They have more energy. That is what temperature is. And so, it's getting hotter and hotter. And so, we have increasing kinetic energy gives increasing temperature. And in fact, the cloud has to radiate about half of the heat, that is about half of the energy that is converted from potential energy to kinetic energy has to be radiated. Well, why is that? Well, consider it's going to be mostly gas. It's got dust in there as well, but it's mostly gas. As it collapses and heats up, the temperature of the gas is going up, and the density is going up. But both the temperature and the density affect the pressure, and so the pressure goes up. And so what we get, we can assume it's an ideal gas, it is more or less, and so what we get is that as it's collapsing, the pressure is going up, and eventually pressure can counteract gravitational collapse. And so as long as the temperature increases, it will stop collapsing. But everything that has temperature emits energy, and so it is emitting this energy out into space, and so it cools, and that allows the pressure to go down, and so it can collapse further, and so it actually has to get rid of some of that heat, and we can detect this in the infrared, and so we actually see protostars forming by their infrared glow. We haven't got it to being flat yet, though. Now, let's consider that it has to conserve angular momentum. So it's spinning about this axis, and it has a mass m somewhere away from it that has a velocity v perpendicular to the spin axis, and then that will have an angular momentum of L, which equals mvr. The angular momentum has to be conserved. So, as the cloud collapses, then it has to spin faster and faster. You can't change the mass, you're not making mass. Your radius is getting smaller, so your velocity must get bigger. And so it spins faster and faster and faster. So now we can go from something that is barely spinning at all to something that's actually spinning quite significantly, like the solar system. But we still don't have it flat. So how do we get it to be flat? Well, oh, I forgot about this. Okay, so the rotation, how much is it going to increase in rotation? So how much faster is it going to go? So here we've got basically revolutions per second. So you've got something that is moving in an orbit around the center of mass, and it is moving at a frequency f, which is the speed divided by the circumference. And so we have the speed is given by this equation, which means that we've got the angular momentum in terms of the mass, the distance from the center of mass, and the frequency of revolution. And so, since L has to be conserved, then as the radius goes down, the frequency of rotation goes up as r squared. And so we can put in some numbers and say, okay, let's say we start from something fairly small, 1/10 of a parsec, and we collapse down to the size of the sun. So saying that most of the material ends up in the sun, it's going to go down by a factor of 10 to the 6. And so what that means is that the cloud will spin up by the square of that, and so we've got a factor of 10 to the 13. So even something that's spinning pretty slowly will have those random motions amplified into something that is spinning very fast. In fact, you wouldn't get it increased this much. You get some friction, and so some energy is lost, and so it doesn't have to spin that fast. But you can easily see how you can get from something that's barely spinning to something that's spinning pretty significantly. Now, the important thing when making it flat is the balance of forces. Now, we've been talking about centripetal force quite a bit in thinking about orbital period. I want to make sure that we understand the difference between centripetal and centrifugal force. And so here I have something that's spinning, and at some point here, P, on the surface of this ball, so we have a globe here, an orb, a sphere. It's spinning about this axis, and so it's spinning around this axis here. And so at this point here, you have a centrifugal force outwards and a centripetal force inwards. And the way I remember this is that from the roots of the words, centrifugal is center fleeing, and I think of it in terms of refugees are always fleeing, and so that's where the fug bit comes from. And so we have centrifugal is pointing outwards, and centripetal is pointing inwards. And so you have the centripetal force, which is associated with the fact that you have something accelerating in a circle, and so the centrifugal force is its equal but opposite reaction. Now, I particularly like this, and I'll read it to you in a second, but many people say, oh, but the centrifugal force is made up, it's not real. Of course it's real. You can see it. You can feel it when you go around the bend and around a corner in a car or on a bike, you lean outwards. It is real. But let me read this cartoon. This is from XKCD, and I love XKCD. So, how do you like my centrifuge, Mr. Bond? When I throw this lever, you will feel centrifugal force crush every bone in your body. You mean centripetal force? There's no such thing as the centrifugal force. A laughable claim, Mr. Bond, perpetuated by overzealous teachers of science. Simply construct Newton's laws in a rotating system, and you will see a centrifugal force term appear as plain as day. Come now, do you really expect me to do coordinate substitution in my head while strapped to a centrifuge? No, Mr. Bond, I expect you to die. By the way, I really like James Bond. Anyway, here we have our spinning globe, and at some latitude, so we've got this point P, and we're at a latitude that's given by this angle phi, and so we're rotating. And at this point, you've got gravity, which is directed towards the center of the globe, of the orb, and you've also got, since it's spinning about this axis, you've also got this centrifugal force, which is acting in this direction. And so gravitational force is just the usual GMM over r squared, but centrifugal force is going to be mv squared over r, but now we have to consider what the r is. So if this thing has a radius r, then the centrifugal force is this r prime is the relevant radius, because that is the radius of the spin. And so it's actually r cos theta, r cos phi, where phi is our latitude. And so we now have that the centrifugal force is mv squared over r cos phi, and again we can do it goes at a constant speed, so 2 pi r cos phi is the circumference of the spin, and the period is p, and so we end up with an equation that looks like this, and we can do some algebra and cancel things, and we get an equation that is the centrifugal force is 4 pi squared, r, which is the radius of the sphere, m, which is the mass at that point, cos phi over p squared. And this is something that is opposing gravity. It's acting in this direction, but gravity is acting in this direction. So what you get is that if you're here, you've got an r prime of 0, so you have no centrifugal force at the pole, and so gravity is acting this way and there's nothing counteracting it. Whereas at the equator, phi is 0, so cos phi is 1, so you have the largest force acting that way and is directly opposite to gravity, and so you get this counteracting force. And so here you can consider, here we've got the globe and it's collapsing under gravity, so gravity is acting towards the center and it's equal in all directions. But if you have something that's rotating, now it's rotating about this axis, you still have gravity acting at the poles by the same amount, but now the gravity at the equator is pushing this way, but now is pulling this way, but now you have a push outwards from the centrifugal force, and you will tend to have things bulging out at the equator. And so this naturally gives rise to a spinning disk, because as you spin this thing around, you've got this thing is spinning and gravity is acting towards the center, but gravity this way is unimpeded by the centrifugal force, whereas gravity this way is impeded, so the action is not as strong, and so you naturally get this happening. And so this is actually what happens if you see people make pizza bases properly, that is not with a rolling pin, and they have a nice little sphere of dough, and they throw it up in the air and spin it around, and it stretches out into a nice disk. This is the same idea, that you're using the centrifugal force to stretch out the dough into a nice disk shape. And so now we've got a nice flattened disk. And so now this is kind of a way of thinking about what's going on. You've got everything's falling in, you've got a star trying to form in the center where the most material is, but you also have this material that's falling down, but it's also rotating, and this rotation will tend to mean that you have material, it's going around in an orbit and it's staying in this disk, whereas material from the top can continue to fall down. And that's it for how we get to a disk-like structure. Next we'll be getting on to how you get planets to form in